The first rule of the cosmos is simple and absolute. Comets always run from the sunday. Their tails, glowing banners of ice and dust, stretching millions of miles through the void, are pushed away by the relentless pressure of solar wind and radiation. This is not theory. This is not hypothesis. This is the fundamental physics that has governed every icy wanderer we have ever observed since Edmund Halley first predicted his comet's return in 1705. Until now, on October 23, 2025, astronomers detected something that should not exist. The interstellar visitor designated 3I Atlas, an object that had already mystified the scientific community with its unprecedented journey from beyond our solar system, had developed a new tail. But this tail was not behaving according to the ancient rules. This tail, a luminous tendril stretching the length of Manhattan, was pointing directly toward the Sunday. The implications of this single observation cannot be overstated. What we are witnessing is either a complete overthrow of cometary physics or something far more profound. An object approximately the size of a city block, traveling at 70,000 miles per hour through the inner solar system, has just announced that it does not obey the laws we thought were universal. And in 4 days, it will disappear behind the sun, hidden from every telescope on Earth, precisely when the physics of orbital mechanics would make any potential maneuver most effective. The question that now haunts observatories around the world is deceptively simple. What is 3I Atlas doing? To understand the magnitude of what we are observing, we must first understand what makes this object so exceptional even before the anti-tail appeared. 3I Atlas is only the third confirmed interstellar visitor ever detected passing through our solar system. The first was Oumuamua in 2017, an elongated object that accelerated away from the sun in ways that defied simple gravitational explanations. The second was Comet Borisov in 2019, which behaved more like traditional comets but still carried the exotic chemistry of its distant origin. Both objects arrived, passed through, and departed, leaving behind more questions than answers. But 3I Atlas is different. From the moment of its discovery, this object has challenged every assumption we hold about what interstellar visitors should look like and how they should behave. Its trajectory brought it not just through the outer reaches of our solar system, but diving deep into the inner planets, passing closer to the sun than Mercury orbits. This is not the path of a cautious visitor. This is the trajectory of an object with purpose. Thank you for being with us. Please subscribe and leave a like. The object's approach has been monitored by every major observatory on Earth and several spacecraft in orbit. Ground-based telescopes tracked its rapid brightening as it plunged sunward. The European Space Agency deployed 2 of its Mars orbiters, the ExoMars Trace Gas Orbiter and Mars Express, to observe the visitor during early October, when it passed relatively close to the red planet. These spacecraft, designed to study Martian atmosphere and geology, turned their instruments skyward to capture what data they could of the mysterious interloper. Dr. Colin Wilson, the project scientist overseeing both Mars missions for ESA, confirmed the observations on September 30th. Both spacecraft had successfully captured images and spectral data of 3I Atlas, though he was careful to temper expectations. The object appeared extremely faint in the Mars Express images, pushing the limits of detection. The spectral analysis from ExoMars, which could potentially reveal the chemical composition of the object's emissions, remains under careful study by ESA teams. Science demands patience, and the processing of such data cannot be rushed when the implications could be this significant. Yet, even as official channels counsel caution and methodical analysis, the drumbeat of anomaly grows louder with each passing day. The Keck 2 telescope in Hawaii, one of the most powerful ground-based observatories in the world, had previously captured spectroscopic data of 3I Atlas that revealed something deeply unusual. The object was emitting significant amounts of nickel in its coma, the cloud of gas and dust that surrounds its nucleus. Nickel emissions from comets are not unheard of, but what made this observation remarkable was what was missing. Iron, which should appear in roughly equal proportions to nickel in natural meteoritic material, was almost completely absent. This is not how nature makes things. Every asteroid, every meteorite, every chunk of primordial solar system material we have ever analyzed follows predictable ratios of elements forged in the hearts of ancient stars. Nickel and iron are cosmic companions, born together in supernova explosions and bound together in the mineral matrices of space rocks. To find one without the other is like finding a shadow without an object to cast it. The ratio observed in 3I Atlas is more consistent with refined alloys, the kind of material that requires processing and selection, the kind of material that suggests manufacture rather than accretion. Professor Avi Loeb of Harvard University has been among the most vocal scientists willing to follow this evidence to its logical conclusion. A distinguished astrophysicist who formerly chaired Harvard's astronomy department, Loeb has built a career on asking uncomfortable questions that challenge scientific orthodoxy. In the case of 3I Atlas, he sees not just anomalous data points, but a pattern of behavior that defies naturalistic explanation. The anti-tail is the latest and most dramatic piece of this pattern. Direct source attribution. Professor Loeb stated in multiple interviews that the tail pointing toward the sun is consistent with preparations for what orbital mechanics specialists call an Oberth maneuver, a powered burn executed at the point of closest approach to maximize the gravitational assist from a massive body. He noted that he finds it highly suspicious that the object will be hidden behind the sun from Earth's perspective precisely at Perihelion on October 29th, the exact moment when such a maneuver would be most effective. The Oberth maneuver is one of the most elegant tricks in orbital dynamics. By firing engines at the lowest point of an orbit, where velocity is naturally highest, a spacecraft can achieve far greater changes in trajectory than the same burn would produce in deep space. It is the physics equivalent of a slingshot, multiplying the effective thrust through careful timing. Every interplanetary probe humanity has launched employs variations of this maneuver. Pioneer, Voyager, Cassini, New Horizons all use the gravity wells of planets and the sun itself to boost their velocity and redirect their paths. It is standard practice for anyone trying to navigate the solar system efficiently. The question that Professor Loeb poses is straightforward. If 3I Atlas were under intelligent control, if it were not a comet but a probe, how would it behave as it approached our sun? The answer, orbital mechanics tells us, is exactly as we are observing. It would dive deep into the gravity well. It would orient itself for maximum efficiency, and it would execute a powered maneuver at perihelion using the combination of thrust and gravity to alter its course with minimal fuel expenditure. The timing of the anti-tail's appearance, just days before this optimal window, aligns with what mission planners would call a braking or attitude control burn. But there is another aspect to the timing that adds a layer of intrigue that cannot be ignored. For approximately 2 months, from late October through late December, 3I Atlas will be positioned behind the sun from Earth's vantage point. Every major telescope in our arsenal, from Hubble to the James Webb Space Telescope to the vast arrays of radio dishes scanning the cosmos, will be blind to this object. We will have no direct observations of what occurs during this critical period. When 3I Atlas emerges on the other side in December, moving outward from the sun toward the outer solar system, we will see only the result of whatever happened in that 2-month blackout. The object that exits may not be the same object that entered. Professor Loeb has not been subtle about his concerns regarding this convenient timing. In statements that have reverberated through both scientific circles and social media platforms worldwide, he has questioned whether there might be institutional reluctance to fully investigate or publicly discuss the implications of what is being observed. His cryptic suggestion that people should consider taking vacations before October 29th has gone viral across multiple platforms, spawning countless theories and interpretations. Some see it as scientific caution about potential but unlikely impact scenarios. Others interpret it as a veiled warning about something far more significant. The statement has the quality of a riddle, saying everything and nothing simultaneously. The reaction from NASA has been unusual enough to fuel further speculation and concern. In a move unprecedented for an object classified as a comet, the agency has activated its Planetary Defense Coordination Office to intensify analysis and tracking of 3I Atlas. This office, established to monitor potentially hazardous asteroids and develop strategies for deflecting any that might threaten Earth, does not typically concern itself with comets, which are notoriously difficult to predict and too fragile to deflect using conventional methods. The activation suggests either an abundance of caution regarding the object's trajectory or concerns that extend beyond traditional impact assessment protocols. The Planetary Defense Network represents humanity's first serious attempt to protect itself from cosmic threats. Following the Chelyabinsk meteor event in 2013, when a relatively small asteroid exploded over Russia with the force of multiple atomic bombs, governments and space agencies recognized the need for better detection and response capabilities. The network includes ground-based observatories, space telescopes, rapid response teams, and the beginnings of actual deflection technology, demonstrated by NASA's successful DART mission that intentionally crashed into an asteroid to alter its orbit. It is a system designed for clear and present dangers. That this system has been activated for 3I Atlas, which poses no calculated impact threat to Earth, according to all current trajectory models, suggests that the object's classification may be under active review. Comets and asteroids, despite both being small solar system bodies, are treated differently by planetary defense protocols because their composition and behavior patterns differ fundamentally. A comet is fragile, a loose aggregate of ice and rock that sublimates and fragments under stress. An asteroid is solid, coherent, potentially deflectable through kinetic impact. Something that exhibits controlled maneuvers falls into neither category and demands new protocols, new frameworks, new ways of thinking about classification and response. The broader scientific community remains divided on how to interpret the mounting anomalies surrounding 3I Atlas. The conservative position, held by many established researchers and institutional scientists, is that we are observing exotic but natural phenomena that will eventually yield to conventional explanations once sufficient data is gathered and analyzed. Perhaps the antitale is caused by unusual plasma interactions in the object's coma, creating electrostatic forces strong enough to overcome the outward pressure of solar radiation. Perhaps the nickel-to-iron ratio reflects an unusual parent body in the object's system of origin, where supernovae created atypical abundances of certain elements. Perhaps the trajectory and timing are coincidental, the result of gravitational perturbations over millions of years of interstellar travel, producing what looks like purpose, but is merely probability playing out across cosmic timescales. These explanations are not impossible. The universe has surprised us before with phenomena that seem to violate known physics, but ultimately revealed new physics instead. Pulsars were initially considered potential alien beacons until we understood them as rapidly rotating neutron stars. Fast radio bursts mystified astronomers until we identified magnetars as their likely source. Gamma-ray bursts seemed impossibly energetic until we recognized them as the birth cries of black holes. The history of astronomy is filled with moments when the extraordinary resolved into the natural, when what seemed impossibly artificial proved merely improbably natural. Yet the history of astronomy is also filled with moments when scientists clung to conventional explanations long past the point where evidence demanded new paradigms. The existence of meteorites was dismissed as folklore and impossible until rocks literally fell from the sky in front of scientific witnesses in France in 1803. Continental drift was ridiculed for decades before plate tectonics became accepted fact. The expansion of the universe contradicted Einstein's static cosmos until observations forced the model to change. Black holes were considered mathematical curiosities rather than physical realities until X-ray astronomy proved otherwise. Science progresses not by assuming the conventional, but by following evidence wherever it leads, even when it leads to uncomfortable conclusions that challenge our most fundamental assumptions. The tension between these perspectives, between caution and courage, between the probable and the possible, is what makes the case of 3I Atlas so compelling as it unfolds in real time. We are watching scientific methodology itself being tested under the most extraordinary circumstances. How much anomaly is required before we must seriously consider explanations that challenge our fundamental assumptions about our place in the universe? How much evidence must accumulate before the radical becomes the reasonable? At what point does Occam's razor, which counsels us to prefer simpler explanations, give way to the weight of data that refuses to fit those simpler models? Professor Loeb has been accused by some colleagues of sensationalism, of leaping to extraordinary conclusions based on incomplete data. His willingness to publicly discuss the possibility of alien technology in connection with both Oumuamua and now 3I Atlas has made him a controversial figure in astronomy. Celebrated by some as a brave truth-teller and dismissed by others as a publicity-seeking provocateur. But his scientific credentials are impeccable and cannot be dismissed. His research on black holes, gamma-ray bursts, cosmological reionization, and early universe physics is foundational to modern cosmology. His willingness to consider unorthodox possibilities comes not from ignorance, but from deep engagement with the equations that govern cosmic phenomena. What Professor Loeb argues, when his position is examined carefully, is not that 3I Atlas is definitely artificial. What he argues is that the hypothesis of artificial origin deserves serious scientific investigation rather than reflexive dismissal based on assumption and prejudice. He points out that we have never actually observed an interstellar probe from another civilization, so we do not know with certainty what one would look like or how it would behave. We make assumptions based on our own primitive efforts at interstellar travel, but a civilization capable of traversing the light years between stars would possess technology so far beyond ours that their artifacts might be unrecognizable to us. We might not see obvious propulsion systems or communication arrays. We might see only anomalous behavior in what appears to be a natural object. The challenge of identifying artificial objects against the vast backdrop of natural phenomena is profound and perhaps insurmountable with current methods. The universe is full of rocks. Trillions upon trillions of asteroids, comets, and planetary fragments orbit stars throughout the galaxy. The vast majority will never be observed, never named, never studied. They are the cosmic background, the noise against which we search for signal. If even 1% of 1% of these objects were artificial, we would still be overwhelmed by the statistical dominance of the natural. The probability of any given object being manufactured is vanishingly small. But the probability of never encountering a manufactured object, given the age and size of the galaxy, depends entirely on assumptions about how common technological civilizations are and how they choose to explore their cosmic neighborhood. The Fermi paradox haunts this entire discussion like a specter at the feast of cosmic optimism. If intelligent life is common in the universe, if technological civilizations arise frequently around the hundreds of billions of stars in our galaxy alone, then where are they? Why have we not detected obvious signs of their existence? Why does the electromagnetic spectrum remain silent despite decades of SETI observations scanning millions of frequency channels? Why do the stars show no evidence of Dyson spheres or other megastructures that should be visible across interstellar distances? The silence is so profound, so complete, that it has led some scientists to conclude we must be alone, or nearly alone, in a galaxy that should be teeming with life if our assumptions about the ease of abiogenesis are correct. But perhaps we are not looking correctly. Perhaps we are searching for the equivalent of smoke signals in an age of fiber optics, looking for technologies that any sufficiently advanced civilization would have abandoned millions of years ago. Perhaps advanced civilizations do not broadcast into space with powerful radio transmitters because they have more efficient means of communication that leave no detectable signature. Perhaps they do not build megastructures because they have transcended the need for vast physical constructions, having learned to do more with less, to exist in ways we cannot yet imagine. Perhaps their presence is subtle, woven into the fabric of natural-seeming phenomena that we observe but do not recognize as artificial. An interstellar probe designed by a billion-year-old civilization might be indistinguishable from a comet to our primitive sensors. It might be deliberately designed to appear natural, to observe without alarming, to gather data on emerging species like humanity without triggering defensive or hostile responses that could contaminate the observation. This is not speculation pulled from science fiction, but rather the logical extension of principles we ourselves employ. When biologists study animal behavior, they use camera traps and remote sensors designed to be unobtrusive. When anthropologists study isolated cultures, they are trained to minimize their impact on the observed society. Why would we expect advanced civilizations to be less sophisticated in their observational techniques? This possibility cannot be dismissed simply because it sounds like science fiction. Science fiction is simply speculation about technological futures that do not yet exist for us. But technology that does not yet exist for us might be ancient history for others. The laws of physics are universal, but engineering is evolutionary. What seems impossible at our current level of development might be elementary at others. The Wright brothers' first flight occurred in 1903. Barely a controlled hop of 120 feet. 66 years later, humans walked on the moon. Our rate of technological acceleration is exponential, not linear. Project that forward not decades or centuries, but millions of years. And the gap between our capabilities and those of a mature civilization becomes unbridgeable to imagination. If 3I Atlas is a probe, whose probe might it be? The nearest star to our sun is Proxima Centauri, 4.2 light-years distant. At the speeds we can currently achieve with chemical rockets, reaching even that closest stellar neighbor would require tens of thousands of years. But 3I Atlas is moving at velocities consistent with interstellar origin, having entered our solar system from the direction of the constellation Ursa Major at speeds far exceeding anything gravitationally bound to the Sunday. Working backward along its trajectory, astronomers cannot definitively identify which star system it originated from. The object has been traveling for so long, potentially millions of years, that the stellar positions have shifted significantly And small perturbations from passing stars over those vast timescales make precise backtracking impossible beyond a certain point. It could have come from anywhere within a vast volume of space, encompassing thousands of star systems. This uncertainty about origin raises profound questions about intent. If 3I Atlas is artificial, is it still functioning according to its original programming, or has it been drifting dead through space for eons? Is it aware of our presence, or are we simply another data point to be cataloged? If it is capable of course corrections, as the anti-tale suggests, then it is still operational, still capable of directed action. That means whatever intelligence designed it, however distant in time and space, is reaching across the cosmic void to interact with our solar system at this precise moment in our history. The timing of this potential interaction is itself intriguing. Humanity has only possessed radio technology for approximately 130 years. We have only been capable of spaceflight for 68 years. We have only had nuclear weapons for 80 years. On cosmic timescales, we have only just emerged as a technological civilization, only just begun to make our presence known through electromagnetic emissions that propagate outward from Earth at the speed of light. If 3I Atlas were launched in response to the detection of our radio signals, it would have had to originate from a star system no more than 65 light-years away, traveling at a substantial fraction of light speed to arrive now. That is a very specific set of conditions. But perhaps the probe was not sent in response to humanity specifically. Perhaps it is part of a network of autonomous explorers distributed throughout the galaxy millions of years ago, programmed to investigate any star system showing signs of interesting chemistry or emerging life. Perhaps thousands or millions of such probes drift through the galaxy, most never finding anything of note, but a few detecting the biosignatures of inhabited worlds and activating long-dormant systems to conduct closer observations. In this scenario, 3I Atlas might be one of countless silent watchers, and Earth might be under observation by multiple such systems without our knowledge. The social and philosophical implications of such a possibility are staggering. If we are being observed by an intelligence vast and ancient, what does that mean for human autonomy and free will? Are we a nature preserve, protected but constrained? Are we a scientific experiment, studied but not contacted? Are we beneath notice, too primitive to warrant direct interaction? Or are we on the cusp of some threshold, some test or evaluation that will determine our future relationship with the broader galactic community? These questions have occupied human imagination for centuries, but never before have they felt so immediate, so potentially answerable. The anti-tale of 3I Atlas represents a possible inflection point in human history. If it is confirmed as artificial, if analysis reveals unambiguous signs of technology, then the central question of human existence, are we alone, is answered. The universe is not silent. Intelligence exists beyond Earth. We are part of something larger, and everything we thought we knew about our place in the cosmos must be reconsidered. But if 3I Atlas proves to be natural, if the anomalies resolve into exotic physics rather than engineering, then the mystery deepens rather than resolves. Because the question remains, where are they? With hundreds of billions of stars in our galaxy and trillions of galaxies in the observable universe, the statistical likelihood of intelligence emerging somewhere, sometime, seems overwhelming. Yet we see no evidence. The stars do not flicker with the shadowy transits of megastructures. The radio spectrum is silent of coherent signals. The universe appears empty of intelligence despite appearing perfectly suited to produce it. This is the paradox that torments astronomers and philosophers alike. Either we are alone, cosmically unique despite the vastness of creation, or we are surrounded by intelligence but unable to recognize it or detect it through some limitation of our technology or imagination. Neither answer is comforting. Both are terrifying in their implications. The emergence of 3I Atlas forces this abstract philosophical debate into concrete, observable reality. Here is an object behaving in ways that challenge natural explanation. Here is an opportunity to test hypotheses about alien technology against actual data rather than speculation. Here is the chance to either confirm or refute one of the most important questions humanity has ever asked. The stakes could not be higher. As October 29th approaches, tension builds in astronomical communities worldwide. Observatories are scheduling maximum observation time on the object before it disappears behind the sundae. Amateur astronomers with backyard telescopes are contributing their own observations to the growing database. Social media is ablaze with speculation, theories, and in some cases, fear. The viral nature of Professor Loeb's vacation comment has taken on a life of its own, spawning everything from doomsday predictions to elaborate alien contact scenarios. The line between rigorous scientific discourse and public panic is becoming dangerously thin. Official sources have been careful in their communications, walking a tightrope between transparency and caution. NASA's activation of planetary defense protocols was announced without dramatic fanfare, framed as a routine enhancement of tracking capabilities for a fast-moving object. The ESA's updates on the Mars orbiter observations have been measured and technical, emphasizing the ongoing nature of analysis and the difficulty of drawing conclusions from limited data. These institutions are aware that premature statements could trigger public alarm, but silence could fuel conspiracy theories about cover-ups and hidden knowledge. The media landscape has fractured into camps. Mainstream science journalism has largely adopted the cautious tone of official sources, reporting the anomalies, but emphasizing that extraordinary claims require extraordinary evidence. Tabloid and sensationalist outlets have embraced the alien probe narrative fully, with headlines screaming about first contact and interstellar visitors. Social media exists somewhere between these extremes, with serious amateur astronomers sharing data alongside wild speculation and fabricated evidence. The signal-to-noise ratio is becoming increasingly poor as the story gains traction. Into this chaotic information environment, individual scientists must navigate carefully. Speaking too conservatively risks being ignored in the noise of more dramatic claims. Speaking too boldly risks professional credibility and public trust if predictions prove wrong. Professor Loeb has chosen to speak boldly, accepting the professional risks in exchange for pushing the conversation forward. His critics argue that he is being irresponsible, elevating hypotheses to conclusions before sufficient evidence exists. His supporters argue that he is being appropriately skeptical of conventional assumptions that may no longer fit the data. Dr. Colin Wilson and the ESA teams represent the alternative approach, methodical and measured. They collect data, process it carefully, submit it to peer review, and only then make public statements hedged with appropriate caveats and uncertainties. This is the traditional scientific method, the process that has served humanity well for centuries of discovery. But it is also slow, perhaps too slow, for the modern information environment where narratives form and harden long before peer-reviewed papers can be published. By the time official analysis is complete, public opinion may already be set, immune to correction. This tension between scientific process and public communication has never been more apparent. We live in an age of instant information, but slow knowledge. Data flows at the speed of light, but understanding requires time, The gap between observation and explanation is filled with speculation, and in that speculation, truth and fiction become difficult to distinguish. The challenge for science communicators is to maintain rigor and honesty while remaining relevant and accessible to public discourse. The object itself cares nothing for these human concerns. 3. I-Atlas continues its plunge toward the sun, indifferent to the debates raging about its nature. It follows its trajectory with mathematical precision, whether that trajectory is determined by gravity and momentum or by something more purposeful. In approximately 96 hours, it will reach Perihelion, the closest point to the sun in its orbit. At that moment, it will be subjected to temperatures exceeding 2,000 degrees Celsius, intense radiation across all wavelengths, and gravitational stresses that would tear apart a loosely bound object. What emerges from that crucible, if anything emerges intact, will tell us something important about what 3I-Atlas truly is. If 3I-Atlas is natural, perihelion will likely result in dramatic fragmentation or complete disintegration. Comets are fragile structures, held together by weak gravitational forces and the frozen cohesion of their ices. When subjected to extreme thermal stress, they crack, split, and sometimes explode into clouds of debris. We have witnessed this process many times. Comet Shoemaker-Levy 9 broke into more than 20 fragments before colliding with Jupiter in 1994. Comet Linear disintegrated completely as it approached the Sun in 2000, transforming from a single nucleus into a stream of rubble. If 3I-Atlas follows this pattern, it will not survive as a coherent object, and the mystery will resolve into a natural, if exotic, phenomenon. But if 3I-Atlas is artificial, if its structure is engineered rather than accreted, perihelion may be precisely what it was designed for. A technological object could potentially withstand conditions that would destroy natural materials through the use of advanced thermal shielding, structural reinforcement, or material science beyond our current understanding. More intriguingly, if the object is indeed preparing for an Oberth maneuver, as Professor Loeb suggests, perihelion is not something to be survived, but something to be exploited. The intense gravity of the Sun, at close approach, provides the perfect condition for maximum efficiency in course changes. A burn executed at perihelion can accomplish trajectory modifications that would require vastly more fuel if attempted in interstellar space. The mathematics of orbital mechanics are unambiguous on this point. The Oberth effect, named after German physicist Hermann Oberth, who described it in 1929, demonstrates that rocket burns are most effective when performed at the highest possible velocity. This is counterintuitive to many people who assume that thrust produces the same change in speed regardless of when it is applied. But in reality, the kinetic energy gained from a burn is proportional to the velocity at which the burn occurs. Fire your engines while moving slowly, and you gain a certain amount of energy. Fire those same engines while moving at maximum velocity near a massive gravitational body, and you gain significantly more energy for the same fuel expenditure. Every space agency in the world uses this principle for deep space missions. When Voyager 2 visited the outer planets, it did not simply fly past them. It timed its closest approaches precisely to execute gravity assists that multiplied the effectiveness of its trajectory. When the Parker Solar Probe dives repeatedly toward the Sun, coming closer to our star than any previous spacecraft, it uses Venus flybys and solar gravity to achieve velocities exceeding 400,000 miles per hour. If you were designing an interstellar probe intended to visit multiple star systems over millions of years, you would absolutely program it to use Oberth maneuvers around every star it encountered. It is simply the most efficient way to travel. The timing of the anti-tail's appearance aligns perfectly with this interpretation. A spacecraft preparing for a major burn would need to orient itself correctly, verify its systems, and potentially begin preliminary thruster firings to fine-tune its approach. The visible tail pointing toward the sun could be exhaust from attitude control systems, the spacecraft equivalent of a diver positioning their body before entering the water. If this interpretation is correct, then the main burn will occur at Perihelion, hidden from our view behind the sun, and what emerges in December will be an object on a significantly different trajectory than the one it entered with. This scenario is testable. If 3I Atlas reappears in December on a trajectory that cannot be explained by gravitational forces alone, if it exhibits velocity changes inconsistent with a purely ballistic path, then we will have strong evidence of artificial propulsion. The laws of physics do not lie. An object cannot change its velocity without applying force, and the only natural force available in space is gravity. Any deviation from a purely gravitational trajectory indicates the presence of non-gravitational forces, which means either highly exotic natural phenomena or artificial propulsion. The challenge will be distinguishing between these possibilities. Comets do exhibit non-gravitational forces through outgassing, where sunlight heats volatile materials that explosively vent into space, creating small but measurable thrust. This is what caused the anomalous acceleration of Oumuamua that so puzzled astronomers in 2017 and 2018. However, outgassing produces specific observable signatures. It creates visible jets and comas. It follows predictable patterns based on solar heating. It produces characteristic changes in spin rate and orientation. If 3I Atlas exhibits trajectory changes without these accompanying signatures, the case for artificial propulsion becomes much stronger. The next 2 months will be a period of anxious waiting for the astronomical community and the growing public audience following this story. From late October through late December, we are essentially blind. The sun is the ultimate occulting disk, blocking all electromagnetic radiation from objects positioned behind it from our perspective. Radio telescopes cannot penetrate it. Optical telescopes cannot see through it. Even neutrino detectors, which can see through almost anything due to the weakly interacting nature of neutrinos, cannot help, because the sun itself is a prodigious neutrino source that would overwhelm any signal from a small object. This enforced blindness feels almost conspiratorial, as if the universe is deliberately hiding something from us. It plays into human tendencies toward pattern seeking and narrative construction. We are storytelling creatures, evolved to find meaning in events, to construct explanations that satisfy our need for coherence. The fact that 3I Atlas disappears precisely when it might be doing something significant is too convenient, too dramatic, too much like a plot device from a science fiction story. This is partly why Professor Loeb's comments about the timing have resonated so strongly. They articulate what many people are feeling, that we are living through the setup for something momentous. But the universe is not a narrative constructed for human satisfaction. Events are not timed for dramatic effect. The fact that perihelion occurs when it does is a consequence of orbital mechanics and the geometry of solar system observation, nothing more. From most other vantage points in the solar system, 3I Atlas would remain visible throughout its passage. If we had substantial infrastructure on Mars or in the outer solar system, we could maintain continuous observation. Our blindness is a limitation of our current technological development and our single-planet perspective, not a deliberate occlusion. This raises an important point about the nature of evidence and observation in the modern era. We are accustomed to instant information, to satellite networks that provide global coverage, to redundant systems that ensure no important event goes unobserved. But in space, we are still primitives, confined to a single vantage point with limited instrumentation and vast gaps in our observational capabilities. The solar system is immense, and we occupy an infinitesimally small portion of it. Most of what occurs happens beyond our ability to detect or observe. We see only the tiniest fraction of cosmic events, the ones that happen to occur in our limited field of view at times when we are looking in the right direction with the right instruments. This humility about our observational limitations should temper both excessive skepticism and excessive belief. We should not dismiss the possibility of artificial objects simply because we have not definitively detected them before. Our search has been brief and limited, but neither should we accept extraordinary claims without extraordinary evidence. The appropriate stance is one of active investigation, of bringing our best instruments and analysis to bear on the question while remaining open to multiple possible explanations. The ESA teams working on the Mars orbiter data exemplify this approach. They are processing spectral information carefully, comparing it against databases of known materials and emission patterns, running simulations to understand what physical processes could produce the observed signatures. This work is painstaking and time-consuming, requiring cross-checking and peer review to ensure accuracy. When they publish their findings, those findings will be as solid as current science allows. They may not be definitive, they may not resolve all questions, but they will represent genuine knowledge rather than speculation. Similarly, ground-based observatories continue to gather data on 3I Atlas as it approaches perihelion. Every observation adds to our understanding of the object's composition, structure, and behavior. Spectroscopic analysis reveals the chemical makeup of the coma. Photometric observations track changes in brightness that indicate rotation rate and surface properties. Radar observations, though challenging at interstellar distances, can potentially reveal information about size and density. Each data point constrains the range of possible explanations, narrowing the field of hypotheses that remain consistent with observation. This is how science actually works, not through dramatic revelations and sudden certainties, but through the gradual accumulation of evidence that slowly tilts the balance of probability towards certain explanations and away from others. It is less satisfying than the narratives presented in popular media, where mysteries are solved in convenient time frames and answers arrive neatly packaged. Real investigation is messy, full of false starts and contradictory data, requiring patience and tolerance for ambiguity. The public, trained by television and film to expect resolution, often struggles with the open-ended nature of genuine scientific inquiry. Yet there is something profound and beautiful in this messiness, this uncertainty. It represents the actual process of discovery, the moment when humanity stands at the boundary between the known and unknown, peering into darkness with insufficient light, but determined to see what can be seen. This is the essence of the scientific endeavor, the willingness to confront mystery without premature closure, to live with questions until answers emerge through evidence rather than assumption. As the hours count down to perihelion, various scenarios play out in scientific models and public imagination. In one scenario, 3I Atlas fragments spectacularly, breaking apart under thermal and tidal stress, transforming from a single object into a diffuse cloud of debris. This would be consistent with cometary behavior and would likely close the book on artificial origin hypotheses. The antitale would be explained as an unusual but natural outgassing phenomenon, perhaps caused by the specific composition and structure of this particular interstellar comet. The scientific community would publish papers analyzing the event, extracting whatever lessons could be learned about interstellar material science and cometary physics, and the case would be filed away as an interesting but ultimately natural occurrence. In another scenario, 3I Atlas survives perihelion intact, emerging on the other side of the Sun in December, structurally coherent and exhibiting no signs of the fragmentation that should have occurred if it were a natural comet. This would be highly significant, but not necessarily definitive. Some asteroids have survived close solar approaches intact, their rocky composition and structural coherence allowing them to withstand conditions that would destroy a comet. If 3I Atlas proves to be more asteroid-like than comet-like in composition, its survival would be unusual given its interstellar origin and observed behavior, but not impossible to explain naturally. The most dramatic scenario involves 3I Atlas, not only surviving perihelion, but emerging on a trajectory that cannot be explained by gravitational forces alone. If the object's post-perihelion path shows evidence of a powered maneuver, if its velocity and direction indicate forces beyond gravity at work, then the conversation shifts dramatically. At that point, the artificial hypothesis becomes difficult to dismiss, and the scientific community would face the extraordinary challenge of confirming or refuting the possibility of alien technology in our solar system. This confirmation process would be rigorous and contentious. Extraordinary claims require extraordinary evidence, as Carl Sagan famously noted, and the burden of proof for artificial origin is immense. Every alternative explanation would need to be exhaustively explored and eliminated. Natural outgassing, gravitational interactions with previously unknown solar system objects, measurement errors, computational mistakes in trajectory calculation, all of these would need to be ruled out before the conclusion of artificial propulsion could be accepted. The process could take years, involving multiple independent analyses and observations. But if that process eventually confirmed artificial origin, the implications would be staggering and immediate. It would represent first confirmed contact with extraterrestrial technology, even if not with living extraterrestrial beings. It would prove that intelligence exists or has existed elsewhere in the universe. It would validate decades of SETI effort and justify continued investment in the search for extraterrestrial intelligence. It would raise immediate questions about the origin, purpose, and capabilities of the probe. It would force humanity to confront its place in a universe that contains other technological civilizations. The geopolitical implications alone would be significant. Which nations or organizations would have authority over interactions with or study of an alien artifact? What protocols exist for such scenarios? The answer is that very few formal protocols exist. The United Nations Office for Outer Space Affairs has guidelines for the detection of extraterrestrial intelligence, but these focus primarily on radio signals rather than physical objects. There is no established international framework for dealing with an actual artifact of alien origin within our solar system. The legal status of such an object under space law is unclear. Could it be claimed, studied, kept secret for national security reasons? These questions, currently hypothetical, could become urgently practical depending on what emerges from behind the sun in December. The months following perihelion could see intense diplomatic activity as nations and international bodies scramble to establish frameworks for unprecedented circumstances. Scientific organizations would need to coordinate observation and analysis across borders. Military establishments would assess security implications. Religious leaders would grapple with theological questions about humanity's place in creation. Philosophers would revive ancient questions about the nature of intelligence and consciousness in new contexts. The psychological impact on human civilization would be profound and unpredictable. For some, confirmation of extraterrestrial intelligence would be exhilarating, a validation of long-held beliefs and hopes that we are not alone in the cosmos. For others, it would be terrifying, challenging fundamental assumptions about human uniqueness and importance. Religious frameworks would face challenges or find new interpretations. Some faiths might embrace the discovery as evidence of divine creation's vastness. Others might struggle to reconcile alien intelligence with theological doctrines centered on humanity's special relationship with the divine. The economic implications could be substantial as well. Markets respond to uncertainty, and confirmation of alien technology would represent uncertainty of the highest order. What capabilities might such technology possess? What knowledge could be extracted from it? What competitive advantages might nations or corporations gain from access to it? The potential for disruption across multiple sectors, from aerospace to material science to energy production, would be enormous. Investment patterns could shift dramatically as capital flows toward organizations positioned to benefit from or study the phenomenon. But we are getting ahead of ourselves. These scenarios remain speculative until 3I Atlas reappears and its post-perihelion behavior can be observed and analyzed. The responsible approach is to prepare for multiple possibilities while avoiding premature conclusions. This is where scientific discipline becomes essential. The ability to maintain analytical rigor, even in the face of potentially revolutionary discoveries. The current moment, these final days before perihelion, represents a unique state of superposition. Like Schrödinger's famous thought experiment, with the cat that is simultaneously alive and dead until observed. 3I. Atlas exists in our understanding as simultaneously natural and artificial, until definitive evidence resolves the ambiguity. We stand at a branch point in the probability tree of human knowledge where multiple futures remain possible, and the next observation will collapse that multiplicity into a single reality. This quantum metaphor is appropriate because it captures something essential about how knowledge works. Before observation, multiple explanations coexist as hypotheses with varying probabilities assigned based on prior knowledge and theoretical frameworks. The act of observation does not create reality, but reveals which of the pre-existing possibilities corresponds to actual fact. Our uncertainty is epistemic, a limitation of our knowledge, not ontological, a fundamental indeterminacy in reality itself. 3I Atlas is what it is, regardless of our observations or theories. Our task is simply to determine which explanation best corresponds to that objective reality. The tools we have available for this determination are limited but sophisticated. Spectroscopy allows us to identify chemical compositions from millions of miles away by analyzing the specific wavelengths of light absorbed or emitted by different elements and molecules. Photometry tracks brightness changes that reveal information about rotation, shape, and surface properties. Astrometry measures precise positions that allow trajectory calculation. Radar can penetrate dust and gas to reveal underlying structure. Each technique has strengths and limitations, but collectively, they provide multiple independent lines of evidence that can be cross-checked and validated. The human element in this process cannot be ignored. Scientists are not dispassionate observers, but people with biases, preconceptions, and emotional investments in particular explanations. Some researchers have built careers arguing for the prevalence of life in the universe and may be unconsciously biased toward interpretations that support that position. Others have staked their reputations on skepticism about extraterrestrial intelligence and may resist evidence that challenges their stance. Peer review and institutional structures exist partly to mitigate these biases, requiring claims to withstand scrutiny from researchers with different perspectives and investments. Professor Loeb has been unusually transparent about his own position and reasoning, making him both admirable and vulnerable. By publicly advocating for serious consideration of the artificial hypothesis, he has opened himself to criticism from those who believe he is overreaching. But he has also demonstrated courage in being willing to consider explanations that much of the scientific establishment reflexively dismisses. Whether his specific claims about 3I Atlas prove correct or not, His willingness to challenge consensus has value. Science progresses, not through unanimity, but through the productive tension between competing ideas, each pushed as far as evidence and logic allow. Dr. Wilson and the ESA teams represent the complementary approach, methodical accumulation of data with cautious interpretation. Both approaches are necessary. Without bold hypotheses, science becomes purely descriptive, cataloging phenomena without attempting to explain them. Without rigorous empiricism, science becomes speculation, disconnected from reality. The productive middle ground involves generating multiple competing hypotheses and systematically testing them against observation, allowing evidence rather than assumption to determine which explanations survive. As October 29th approaches and 3I Atlas makes its closest approach to the Sun, observatories around the world are positioned for final observations before the object disappears from view. The last images and spectra captured before occultation will be analyzed with extraordinary care, searched for any detail that might provide additional clues about the object's nature. Amateur astronomers contribute their observations as well, creating a distributed network of sensors that supplements professional facilities. In the age of affordable telescopes and sensitive cameras, citizen science has become a legitimate contributor to astronomical research. Social media amplifies both the legitimate science and the noise surrounding it. Hashtags related to 3I Atlas trend globally as people share observations, theories, and in many cases, fabricated images purporting to show details that exceed the resolution of any existing telescope. The challenge for informed observers is distinguishing real data from convincing fakes. Image manipulation software has become sophisticated enough that creating realistic-looking astronomical images is relatively straightforward for anyone with basic technical skills. Without careful verification of sources and independent confirmation, the information ecosystem becomes polluted with false data that muddies genuine understanding. This is not a new problem. Hoaxes and misidentifications have plagued astronomy since ancient times. The canals of Mars, reported by respected astronomer Percival Lowell in the early 20th century, turned out to be optical illusions combined with wishful thinking. The WOW signal, detected by SETI in 1977, generated enormous excitement, but has never been detected again and remains unexplained. The Martian meteorite, ALH 84001, claimed in 1996 to contain evidence of fossilized bacteria, sparked intense debate that ultimately concluded the evidence was ambiguous at best. Each of these cases involved genuine scientists working with real data who nevertheless reached conclusions that could not be sustained under continued scrutiny. The lesson from these historical examples is not that extraordinary claims are always wrong, but that they require extraordinary caution. Confirmation bias is powerful. We tend to see what we expect or hope to see. We interpret ambiguous data in ways that support our preferred explanations. These tendencies are not malicious, but cognitive, part of how human brains process information efficiently. Science compensates for these biases through methodology, requiring reproducibility, independent verification, and explicit consideration of alternative explanations. When these safeguards are bypassed or weakened, errors proliferate. In the case of 3I Atlas, multiple safeguards are in place. Observations come from multiple independent observatories, using different instruments and techniques. Data analysis is performed by different teams using different methods. Results are shared openly in preprint servers and peer-reviewed journals, where they can be scrutinized by the broader scientific community. This distributed, redundant approach to knowledge generation is science's greatest strength. It makes deception or error difficult to sustain because any claim must survive multiple independent challenges. Yet even this robust system has limitations. Complex data requires interpretation, and interpretation involves judgment calls about which models to use, which assumptions to make, which uncertainties to emphasize. Two competent scientists examining the same data can reach different conclusions if they make different methodological choices. This is not failure, but rather the reality of working at the boundaries of knowledge where clear answers are not yet available. Over time, as more data accumulates and understanding deepens, these differences typically resolve. But in the moment, ambiguity and disagreement are normal and expected. The question of what constitutes sufficient evidence for extraordinary claims is itself contested. The standard invoked by Carl Sagan, extraordinary claims require extraordinary evidence, sounds reasonable but lacks specificity. How extraordinary must evidence be? Who decides? What makes evidence extraordinary rather than merely strong? These questions have no universal answers. Different scientific communities and different historical moments have applied different standards. Generally, claims that overturn more established knowledge require stronger evidence than claims that extend existing frameworks in modest ways. But the boundaries are fuzzy and subject to debate. If 3I Atlas proves to be artificial, the evidence required to convince the scientific community would need to be overwhelming and unambiguous. Simple trajectory anomalies, even if significant, might not suffice because natural explanations involving outgassing or measurement error could still be proposed. More definitive would be clear artificial structures visible in high-resolution images, radio signals emanating from the object, or spectroscopic signatures of synthetic materials that cannot be produced by natural processes. Even better would be direct interaction, though the risks and ethical implications of attempting to communicate with or interfere with a potentially alien artifact would be substantial and would require careful international coordination. The alternative scenario, where 3I Atlas proves to be natural but exotic, would be scientifically valuable even if less dramatic. Understanding how interstellar comets form, what compositions they possess, how they behave under extreme conditions, all of this contributes to our knowledge of planetary system formation and the distribution of materials throughout the galaxy. Every interstellar visitor provides a sample of material from beyond our solar system, a free delivery of information about other stellar environments. These objects are scientific treasures, regardless of whether they prove to be natural or artificial. The broader context of this event extends beyond 3I Atlas itself. We are living through the early decades of a new era in astronomy, one where interstellar objects are detectable and observable. Before 2017, no confirmed interstellar visitor had been identified. Now, we have 3 in 8 years. This increasing rate of detection reflects improving telescope capabilities and survey programs designed to identify fast-moving objects. The Large Synoptic Survey Telescope, soon to begin operations, will dramatically increase our ability to detect such objects. Within a decade, we may be observing dozens of interstellar visitors per year. This coming wave of detections will provide statistical context currently lacking. With only 3 confirmed examples, we cannot determine what is typical and what is anomalous for interstellar objects. Are nickel-rich compositions common or rare? Are unusual trajectories frequent or exceptional? Do anti-tails occur regularly under certain conditions? Or is this genuinely unprecedented? As sample size increases, these questions will become answerable. Patterns will emerge, norms will be established, and genuine anomalies, if they exist, will stand out more clearly against the baseline of natural variation. In this larger context, 3I Atlas may prove to be either the most important astronomical discovery in human history or simply the most thoroughly observed interstellar comet to date. Both outcomes have value. Both advance human knowledge. Both contribute to the great project of understanding our place in the cosmos. The uncertainty about which outcome will prove true is uncomfortable, but also exhilarating. We stand at a moment of genuine discovery where the answer is not yet known, and observation will reveal new truth. The philosophical implications extend beyond science into questions about knowledge itself. How do we know what we know? What level of certainty is achievable? When should provisional conclusions be drawn versus waiting for more complete information? These epistemological questions are not abstract, but practical, affecting how we respond to potential discoveries. Premature certainty leads to embarrassment when later evidence contradicts early conclusions. Excessive caution leads to paralysis, unable to draw any conclusions from even strong evidence. The appropriate middle path requires judgment, experience, and willingness to update beliefs as new information becomes available. This moment in history, these final hours before 3I Atlas disappears behind the sun, carries weight that transcends the immediate scientific questions. We are participants in a story that began when the first humans looked up at the night sky and wondered what lay beyond Earth. For millennia, those questions could only be answered through mythology, philosophy, and imagination. The stars were unreachable, their nature unknowable through direct observation. Gods and spirits inhabited the heavens in human imagination because no empirical method existed to determine what actually existed there. The scientific revolution changed this fundamentally. Galileo's telescope revealed that the moon had mountains and valleys, that Jupiter had moons, that the Milky Way resolved into countless individual stars. Each discovery pushed back the boundary of the known and revealed new mysteries beyond. Newton's laws showed that the same physics governing falling apples also governed planetary orbits. Spectroscopy revealed that distant stars were made of the same elements as Earth. Einstein's relativity unified space and time into a single geometric framework. Quantum mechanics revealed the probabilistic nature of reality at microscopic scales. Each of these advances represented a triumph of human intellect and persistence. Each required abandoning comfortable assumptions in favor of evidence-based understanding. Each met resistance from those invested in older paradigms. And each ultimately prevailed because evidence accumulated beyond the point where alternative explanations remained tenable. This is the process we are witnessing with 3I Atlas, the grinding gears of scientific methodology working to transform observation into understanding. The difference now is that this process unfolds in real time before a global audience. Previous scientific revolutions occurred slowly over decades or centuries, with knowledge gradually percolating through academic communities before reaching public awareness. But in the internet age, observations are shared instantly. Preprint servers make scientific papers available before peer review. Social media allows direct communication between researchers and public. The boundary between professional science and public discourse has become permeable in ways both beneficial and problematic. The benefit is democratization of knowledge. Anyone with internet access can read the same papers, view the same images, and follow the same debates as professional scientists. Expertise still matters, but it is no longer gate-kept behind institutional walls. Amateur astronomers make genuine contributions. Citizen scientists analyze data. Public engagement with science reaches levels unprecedented in history. This represents a kind of intellectual renaissance, where curiosity about the natural world is accessible to anyone willing to invest effort in understanding. The problem is that accessibility does not confer competence. Understanding scientific papers requires training in reading technical literature, evaluating methodology, recognizing limitations and uncertainties. Without this training, It is easy to misinterpret findings, to mistake preliminary results for established fact, to miss crucial caveats and qualifications. The result is an information ecosystem where accurate science coexists with misunderstanding and deliberate misinformation, all presented with similar aesthetic formatting and rhetorical confidence. Navigating this environment requires media literacy and critical thinking skills that are not universally distributed. Distinguishing credible sources from unreliable ones, recognizing logical fallacies and rhetorical manipulation, understanding the difference between correlation and causation, these abilities must be cultivated through education and practice. In their absence, people are vulnerable to believing whichever narrative is most emotionally satisfying or most aggressively promoted, regardless of its correspondence to evidence. The case of 3I Atlas exemplifies these challenges. The core facts are reasonably clear and well documented. An interstellar object is passing through the inner solar system. It has developed an unusual tail pointing toward the Sunday. Its spectroscopic signature shows anomalous nickel to iron ratios. NASA has activated planetary defense protocols. These facts are not in dispute. What remains contested is their interpretation. Do these observations indicate artificial origin, exotic natural phenomena, or something else entirely? This is where expertise and judgment become essential, where the ability to evaluate competing explanations based on their explanatory power and consistency with broader knowledge makes the difference between understanding and confusion. Professor Loeb's contribution to this debate, regardless of whether his specific hypothesis proves correct, is his willingness to articulate and defend a minority position that most scientists are reluctant to seriously consider. The taboo against discussing extraterrestrial intelligence in professional astronomy is real and has historical roots. Too many careers were damaged by association with UFO research or SETI when those fields were considered fringe. Too many scientists witnessed colleagues dismissed as cranks for taking such questions seriously. The result is a kind of collective caution that may have prevented careful consideration of legitimate anomalies. Breaking this taboo requires senior scientists with established credentials and institutional protection. Junior researchers cannot afford the professional risk. But someone like Professor Loeb, with tenure at an elite institution and a distinguished publication record, can speak freely without endangering his career. His willingness to do so creates space for other researchers to engage with questions they might otherwise avoid. This is a valuable service to science, even if his specific claims about 3I Atlas or Oumuamua ultimately prove incorrect. Dr. Wilson and his colleagues at ESA provide the necessary counterbalance, representing institutional science at its best. Careful, methodical, unwilling to overreach their data, they embody the virtues of patience and rigor that have made modern science so successful at generating reliable knowledge. Their approach may be less exciting than bold speculation, but it is more likely to produce lasting insights that withstand the test of time and replication. Both approaches, the provocative and the cautious, are necessary for healthy scientific discourse. As the clock counts down to perihelion, we might reflect on what makes this moment so compelling beyond the immediate scientific questions. Part of the fascination is existential. The possibility that we might not be alone in the universe touches something deep in human psychology, our need to understand our place in the larger scheme of things. For most of human history, we imagined ourselves at the center of creation, special and unique. The Copernican revolution displaced us from the center, revealing Earth as one planet among many. The discovery of the true scale of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, made our cosmic insignificance undeniable. Yet we remain the only confirmed intelligence the only known instance of matter organizing itself into self-aware complexity, capable of understanding the universe that created it. This tension between cosmic insignificance and unique achievement defines much of modern existential anxiety. Are we remarkable or trivial? Special or random? The answer matters for how we understand ourselves and our future. If intelligence is common, then we are one instance among many, and the universe is rich with minds contemplating existence. If intelligence is rare or unique, then we bear a special responsibility, as perhaps the only way the universe can know itself. The discovery of artificial objects from other civilizations would resolve this question decisively. We would know that intelligence arises elsewhere, that the universe produces minds beyond our own. This would be simultaneously humbling and exhilarating. Humbling because we would no longer be unique. Exhilarating because we would have cosmic companionship, proof that the evolutionary path from chemistry to consciousness is not impossibly improbable, but a natural outcome given sufficient time and suitable conditions. The implications for human purpose and meaning would be profound. Religious frameworks that place humanity at the center of divine attention would need revision or reinterpretation. Philosophical systems built on human exceptionalism would require rethinking. Our entire self-conception as a species would shift, accommodating the reality of other minds, other civilizations, other ways of being intelligent. This could be traumatic or liberating depending on how we approach it, but it would certainly be transformative. Conversely, if 3I Atlas proves natural and we continue to find no evidence of extraterrestrial intelligence despite improving detection capabilities, the Fermi paradox deepens. The silence of the cosmos becomes more difficult to explain. We would be forced to consider possibilities both wonderful and terrible. Perhaps intelligence is so rare that we are effectively alone in the observable universe, a cosmic accident unlikely to be repeated. Perhaps intelligence is common but short-lived, inevitably destroying itself through war, environmental collapse, or technological mishap before achieving the stability necessary for long-term survival. Perhaps intelligence transcends in ways that make it undetectable to us, ascending to forms of existence that leave no observable trace in the material universe. Each of these scenarios has implications for human future. If we are rare, we have an obligation to survive and flourish, as perhaps the only consciousness in our cosmic neighborhood. If intelligence is typically short-lived, we must understand and overcome the great filters that destroy emerging civilizations. If transcendence is possible, we might aspire to achieve it ourselves, escaping the limitations of biological existence into something greater. These are not idle speculations, but questions with practical consequences for how we organize society, allocate resources, and plan for long-term survival. The truth is that we do not yet know which scenario describes reality. 3. I-Atlas may provide crucial evidence, or it may prove to be one more ambiguous data point in an ongoing investigation that spans decades or centuries. Science does not always provide quick answers. Some questions require generations of sustained effort before resolution. The existence of extraterrestrial intelligence may be one such question, answerable only through patient accumulation of observations across many years and many potential signals or artifacts. What we can say with confidence is that we are asking the right questions and using appropriate methods. The scientific approach, with all its limitations and human imperfections, remains the most reliable tool humanity has developed for distinguishing truth from falsehood about the natural world. It is not infallible. It makes mistakes. It proceeds slowly and sometimes backtracks. But it is self-correcting in ways that other knowledge systems are not. Evidence eventually prevails over assumption. Reality ultimately constrains theory. This is why science has been so successful at expanding human knowledge and capability over the past few centuries. As 3I Atlas makes its closest approach to the Sun, disappearing from our view into the blinding glare of our star, we enter a period of enforced patience. For 2 months, we can only wait and wonder. When the object reemerges in December, emerging from behind the Sun into the observational reach of our telescopes, we will learn something important. The object will be on a trajectory, moving at a particular velocity in a particular direction. That trajectory will be calculable, and it will either match the predictions of gravitational mechanics, or it will not. If it matches, 3I Atlas is likely natural. If it deviates significantly, we have a genuine mystery demanding explanation. The waiting will be difficult for those following this story. Humans prefer action to patience, answers to uncertainty, but some processes cannot be rushed. The object moves according to physics, not human preference. The Sun occludes according to geometry, not our desire for constant observation. Reality proceeds at its own pace, indifferent to our anxiety and curiosity. This indifference is not cruelty, but simply the nature of a universe that exists independent of human concerns. In this waiting period, we might productively reflect on what we hope to discover and why. Do we want 3I Atlas to be artificial? Would proof of extraterrestrial intelligence be welcome or frightening? Would it change how we live our lives, or would it be absorbed into the background of interesting facts that do not affect daily existence? These questions reveal much about human psychology and our relationship with the unknown. Some people desperately want to believe we are not alone, finding the alternative too isolating to bear. Others prefer cosmic solitude, finding the idea of alien intelligence threatening to human autonomy and significance. Neither preference determines reality. The universe is what it is, regardless of our hopes and fears. This is both liberating and sobering. Liberating because truth is not subject to popular vote or emotional appeal. Sobering because we must accept whatever reality reveals, even if it contradicts our preferences. Scientific maturity involves developing this acceptance, the ability to embrace evidence-based conclusions, even when they challenge cherished beliefs or comfortable assumptions. The story of 3I Atlas, whatever its ultimate resolution, will be remembered as a moment when humanity confronted questions that have haunted us since we first developed self-awareness. We have always looked at the stars and wondered. Now we have the tools to potentially answer those ancient questions through observation and analysis rather than speculation and myth. This represents an extraordinary achievement, worthy of celebration regardless of what we discover. In 4 days, the object will reach Perihelion. In 2 months, it will reemerge, transformed or unchanged by its passage through the inferno of solar proximity. Until then, we wait, suspended between possibilities, living in that rare moment when the future remains genuinely undetermined from our perspective. The answer exists, written in the trajectory of a small object moving through space, but we cannot yet read it. When we can, when December arrives and observations resume, we will take one more step in the endless human journey toward understanding the cosmos that gave us birth and the place we occupy within it. Whatever we discover will not be the end of mystery, but the beginning of new questions. This is the nature of knowledge, each answer revealing new puzzles, each resolution opening fresh investigations. The wonder is not diminished, but deepened by understanding. The cosmos becomes more marvelous, not less, as we learn its workings. And perhaps, if we are fortunate and persistent, we may someday know whether we explore this magnificent universe alone or in the company of other minds as ancient and strange as we can barely imagine. Thank you for being with us. Please subscribe and leave a like.